approach find better, and also matrix approach. Now for chapter 3B, and Gauss-Markov theorem ensures that these least square regression coefficients are the best. We also study random error epsilon, and so in chapter 3B, we try to estimate epsilon. We actually estimate the constant, the variance of the random error. Okay? And for maximum likelihood estimation in the distribution theory, you need this assumption. That's why I have two arrows here pointing to maximum likelihood estimation and distribution theory. Okay? And we learned that if you do maximum likelihood estimation, they are identical except for sigma squared, where the degrees of freedom is slightly different. N minus P, N minus K plus 1. Of course, when we study the multiple linear regression model, this random error is not a factor. So I'm talking about the distribution of the random vector. This random vector has mean 0 and variance covariance matrix sigma squared by n. But this is actually something we learn in mathematical statistics. I know that some of you don't have this course taken in, so you will need to work on your own. Some of it, especially the distribution theory. In fact, distribution theory, for the results that I stated, you won't learn in mathematical statistics also. It's slightly beyond. So I will make a summary of the results. So today, I'm going to talk about chapter 2C. Chapter 2C, we are talking about that. There's a know how to test that. Okay, this is the last range. Last range is the proportion of degrees in y, explained by the regression model. So, what here is the decomposition of the variance. Well, so let's go ahead and talk about this decomposition of variance. Just a tip. I actually have done the decomposition for you. And it's on page 8 to 9 of chapter 3. Because we are going to use the result. This is actually page 8. So here, I actually give you the proof for the decomposition of the variance. So I started with SS ratio, right, in terms of And you can explain this, as I've explained in the last lecture. We will get this equation. SS residue is the total derivation minus okay. So, actually forms the basis of the composition of variance that we are going to discuss today. So today, I want to talk about the decomposition of variance. And overall model is something we have not done before. So far, we have talked about individual testing individual expression coefficient. But now, the overall model is a model appropriate. And then, today we are going to go for multiple linear model. And then look at test confidence interval for individual expression. Well, as you know, I think in tutorial 2, I want you to derive some theory for linear regression. So, yeah, I will discuss this tutorial. So now let's look at the decomposition of variance. Decomposition of variance is this. It means decomposed into two components. One is the sum of residue. The other one is the sum of due to the regression. Okay, moving on. And I like you to pay this one. Because the book is not similar. That's why I make my own notes for you. When you go back and read the book, you will find it easier. Alright? So, the first one, what I did in the last section, chapter 15, we found that SS residue, and we written as y prime y transpose y minus beta transpose y. So that's what we got when we Why do I want to do that? Well, let's take a look. Y transpose y is, a vector. It's the total variation in y. This is uncorrected. But if you check ny bar square, what you found is this. So this is a simple exercise. I believe you can do it easily. Just expect this. You will find that these two are the same. Right? So this is the uncorrected variation in y. This is the corrected variation in y. Corrected by this. On the other side, excess residue stays the same. And here, we have this. So my bar where you see here. So let's move on. Well, so my bar. So this quantity is denoted by SST. SS residue is the sum of square residue. That one we understand. This one we also understand. So what is this? This is the sum of square due to the regression model that is given. If the model given is good, the residue, sum of square residue, should be very small, and the total variation can be explained by the regression model. That's what it is. If the filter line is not good, sum of square residue can be very large, and this is very small. So it shows that the regression line filter is not good. So this is called sum of square due to regression. So I have written here for you. In fact, it could be technically correct. This is called correct. Now sometimes I can call this. When I say total sum of square, I know I'm referring to the correct total sum of square. Correct by this. Residue sum of square. You start from the sum of square residues. You can show that it is equal to this. This is the sum of square due to the regression model. So this completes the decomposition. Let's call decomposition variance. Right? So now let's take a look. So we have to compose the variance. Now I want to know how can I test the overall full model. Is it appropriate? So let's start with the multiple linear regression model again. Here is your vector observed response. This is your vector regress. Yeah, extension regressor is the regression. Here's the error vector. Well, error vector is assumed to be a random variable. Vector 0 and the variance covariance matrix. So this variance covariance matrix is sigma squared times the identity. That means off-diagonal elements are 0. For multivariate normal distribution, if the off-diagonal elements are 0, it means all the elements here, they are independent. In general, covariance equal to 0 does not imply independence. But for multivariate normal covariance 0 implies independence. So the next thing to know is what is the degrees of freedom for each case. So here I have K plus 1 regressors. So this means And then beta naught is the interceptor. So the total number of regression coefficients is k plus 1. Okay. So what's the decrease of freedom for SST? There's n minus 1 because there is a constraint of y bar. You know, sum of y minus y bar must be 0. So that's a constraint. No, sum of square of this one. The decrease of freedom is n. Because all the y's can be any one. That's a constraint. So the decrease of freedom is n. But if you look at the corrected sum of square, the decrease of freedom is n minus 1 because this constraint, sum of y I minus y bar must be 0. Now, how about residue? Residue, to estimate the residue, you need to estimate beta naught, beta 1. I think there's a problem in the tutorial. So there are k plus 1 parameters you need to estimate. And so this imposes k plus 1 equation or constraint. So in other words, the degree of freedom will be k plus 1. Now here, then SSR, the degree of freedom, will be obtained by subtraction. N minus k plus 1, which is equal to So next, we want to talk about testing overall fit. And I don't know how to Why is it that I don't test beta naught? Beta naught is not associated with any rested beta. Beta not in general. No, beta not actually is intersect. You know, if you look at simple linear regression, intersect. In fact, here is also the intersect on the y-axis. In general, this quantity is not equal to 0. So if you include beta naught is null hypothesis, you are going to reject your null hypothesis all the time. Because beta naught is not 0. Okay? So that's what we want to test. And this decomposition of variance will give us a way to do that. We need that to be able to test the overall field model. So let's take a look at this. Again, let's take a look at several scenarios. So a given data set has a constant, you know, once I mentioned, has a constant. Well, this is constant. These two exchange, depending on how well the regression model is fitted. So how about SSR is with respect to SS ratio? Depends on how close the constant to the regression model. So let's look at situation 1. All the points fall on the actually on the point. Then SSR is 0. SSR is 0. Then SS residue is 0 because there's no residue. SSR will then be SSD. In other words, all the variation in Y can be explained by the regression. There's no regression to 0. how SSR varies according to the system, how this ratio changes with the system model. So it now makes sense to use this ratio here for testing the hypothesis. Well, if H naught is 2, suppose it doesn't depend on order at all, then SSR will be small, and the ratio will be small. But if the order is useful somehow, then the ratio will be large, and will be rejection zone. So that's the idea behind testing overall model using the analysis. But we can't do this. Why? Because there's a simple reason why. Because this ratio, we do not know what it is. Actually, we know what it is. It's not friendly. However, by dividing SSR by this SS residue divided by degrees of freedom, A plus 1 by A is a number of parameters. If I do that, if I take this ratio, the numerator is now called mean square regression, and the denominator is mean square of residue. And this is estimate of the experimental error. Experimental error. So we can use this. We can use it. And I think it's pretty fine.
Sorry, say again. I forgot I set my ringtone, but I can Spotify song now. Sorry, please if you for some dumbass things, not even. Just not even. What these fucking things? This is microseconds, 1, 2, 3, 4, 5, 6, 64 milliseconds. Wait, shit, I didn't see this. Yeah, it's K. No, it says 4. This has 4. Yeah, it's not. It's not. Believe now you probably will learn the same as if you stayed.
All right. So I hope you understand why we are not using this ratio directly. The logic is good. Here, we are still using the ratio, but we just use, we divide them by their degrees of freedom, so that the denominator and the numerator both have chi-square distribution. And because of that, the ratio follows the F distribution. According to one of the results in distribution theory that I summarized for you in chapter 3B. So that's what we use to get this F statistics. Now, so the logic is quite simple. We are using the variance of the experimental error to test how big this mean square regression is. And the degrees of freedom, of course, follows k and n minus p. It follows when the hypothesis is true. The null hypothesis is true. This F statistics follows the F distribution. And so, you can reject the null hypothesis. So, suppose this is F, then this quantity here, this is alpha. So, this quantity is the F percentile. So, we reject it this F is too large, all right? And this decomposition of variance and the test can be summarized neatly into a paper, commonly known as analysis of variance paper. It shows you the source of variation, total, can be broken down into regression and residue. So that is a sum of square. That's the degrees of freedom. So if you have 3 regressive variables, excluding beta naught, alright, as I've explained. So square residue is n minus the total number of regression coefficients. So that's what happened. And then you divide this by this. Get the F statistics. So in R, you will also print a p-value for the test. P-value is a better way, slightly, I think, better way to test it. So next, I'm going to use the delivery time data to show you how to find this F naught using first principle. Okay, using the first principle, and also using the LM model. So, for example, I want to test overall field model. I calculate beta hat transpose times x transpose times y. That is dxy. Sum of square residue is beta xy minus n square sum of y square divided by time. Sum of square residue is transpose of y times y minus dxy. After that, you can calculate F naught. F naught is SSR divided by 2 because there are 2 regressive variables, case and distance. How many regression coefficients are there? 3, including beta naught. So that's why the degrees of freedom is 2, and the degree of freedom for sum of square residue is n minus 3. 3 regression coefficient. So then, using this Pn, this calculates the F percentile, not the F percentile, but the p-value based on the F distribution. So you can search for Pn and try to understand it a bit. This type question mark Pn, it will show you. And this is for those who want to practice manipulation of data. If not, you can go straight to ANOVA. So here I'm fitting a model. Case plus distance. But this ANOVA will not give me the test that I want for testing the overall model. In order to test the overall model, I need to compare this model with this. This means what? This means you are not fitting with anything. You are actually fitting with beta naught, a constant. So here, we try to understand, see when you fit this, you will also include beta naught, but it's beta naught. So you take the difference between these two to test for case and distance. So that's how you can test for overall model. This one. This limit. So you can look at all the output. The p-value is very small. So it shows that the model is significant. So we will reject H0. So what is H0 here? So what's the model? Did I write down the model? Let me see. I did not write down the model, but I think earlier we did. So the model is y equal to beta naught plus beta 1 times case plus beta 2 distance. Here, I want to test whether beta 1 is equal to beta 2 equal to 0. Both of them 0. And the alternative hypothesis is at least one of beta 1 and beta 2 not 0. So that's the alternative. So when your p-value is small, you reject the null hypothesis and you say that, well, we now know that not everyone is 0. So the test overall model tells us this. It tells us that at least one of them is not 0. Which one? We don't know. So you need further tests. Maybe one of them, maybe both of them. But if you do not reject H0, then quite likely this will be true. And it simply means your model is pretty much useless. Okay? Because it says, hey, your response does not depend on your regressive. So, like what I say, you need to, I think the slide has been messed up a bit. I want to move it down. Yeah. So, where I hold it. So this ANOVA statement allows us to test the two parameters at the same time. This is a p-value obtained using this statement by comparing the model based on beta naught and the model based on all the betas, beta naught, beta 1, and beta 2. So that's what happened. Well, so if you have to do by hand, this is what you do. Yeah, this is what I got from the textbook. Pretty much useless because nobody does it by hand anymore. But for those who enjoy doing it by hand, please try it. So my emphasis is understand the theory, use R for application. How do you calculate all this? It's not important. It's a simple calculation. That will not be my emphasis for this course. Okay? My emphasis is for you to understand the theory and apply it using R. That's the emphasis. But sometimes it's good to know how all these things come about. That's why I show you this slide, so that you will understand how all these things are derived. Of course, I've also shown you how to derive it using the R program, R coding. This is what I prefer actually. Alright? But if you are not so familiar with R, you can try this. It's not my preference, okay, for this course. But if you like it, it's fun. I can't even make it better. Alright. Now, let's look at another example. This example is about the cholesterol, a data example. Here, remember, cholesterol increases with age, right? And there's a slight curvature. You can fit a straight line model to it, but the fit is not so good because the mean square error is larger than the one that is based on the quadratic model. So here, if I say LM cholesterol versus 1 here, filter 1, so I'm comparing age. But this is, for simple linear regression, I actually don't need this statement. I can just say ANOVA this. Yeah? But just to show you, exactly what's happening is you are comparing this with beta naught. Yes, beta naught and beta 1. Yes, beta naught. So subtract that. So you subtract this subtract this. 1 degree of freedom, and that is your p-value. Now, you can see that. So what am I doing? I'm testing the fit of a straight line model. What happened to the p-value? Very small. So what does this example tell us? This example tells us, whenever you get a small p-value, don't get too excited. Don't think that's the end of your problem. Don't think you have found the best model. It simply means there's strong evidence that the linear component, the linear dependency exists. It does not tell you whether this model is good or not. In fact, an incorrect model can also yield a very small p-value. So using p-value as a gauge of whether a model fitted is good or not is not such a good idea. Okay? So life is not so simple in regression. Look at this. Is there any difference in the p-value when I fit a quadratic model? Here is h. I introduce h squared. The p-value is also very small. Is there any difference between these two? Nothing. 10 to the power minus 40, 10 to the power minus 60. There's no difference. Yeah, it's like talking about 0.001 cent or 0.01 cent. Is there any difference? Which one do you like if I want to give you one of these amounts? 0.0001 cent or 0.01 cent? Does it matter? Of course not, right? After I give you that amount, you can't even buy anything. Yeah? So it doesn't make sense. So, remember this. But we know, how do we know the model is good? Yeah? We know the model is good. We can't tell from the p-value. That's the point that I'm driving at now. So to tell whether a model is good, in this case, there's a simple solution. Make the plot, draw the horizontal, straight line model there, and then the quadratic model, and compare. Look at it visually. And whichever fit the data better, is better. But is there any other way to do it? Here we are talking about, a two-dimensional plot. Sure, I can plot the data. What if I have 10 regressive variables? How am I going to assess whether a model fitted is good or not? Plotting won't help. And in fact, in the last lecture, I showed you that scatter matrix diagram can in fact lead you to incorrect conclusion. It does not show you the true thing. Yeah? So, is there any other way to check it? Yes, there is. That's called adjusted R squared. That's one way. Another way actually simply is you look at the mean square error. Look at how small it is. So, so we will talk about R squared and adjusted R squared a bit later. But let me just give you a brief review of what we've done. Today, we look at the composition of variance. It means this. And in fact, the derivation is based on chapter 3b, and then we got that. And from that decomposition, we can test overall fitted model. And let's take 5 minutes break. After the break, we will talk about R squared and adjusted R squared for overall fitted.
Saves nothing. Why? What the fuck?
So as you can see, the p value for the overall model is not a good guide to whether the model figure is adequate. For simple cases, you can draw a graph and look at how well the model is fitted. But for more complex, more highly dimensional, or for multiple linear regression model with more regressive variables, you really need a numerical summary. And that's called adjusted R squared. So that's what I want to talk about now. So let's go and take a look at this R squared. Alright. First of all, point number one. R squared and adjusted R squared are two measures for assessing the overall adequacy of the model. What is R squared? R squared is sum of square regression over sum of square total. So if the model fitted is good, all the points are close to the fitted model, your SR will be large. Or you can look at R squared in terms of sum square residue. Sum square residue measures the discrepancy between the observed points and your fitted model. So if the fitted model is good, SS residue will be small. So this will be close to 0. It's at most 1, or it can be 0. So for a perfectly fitted model, sum of square residue is 0. And so R squared is 1. R squared 1 means all the variation in 1 can be explained by the fitted model. Now, why is it that Y must vary? Because it follows the regression model. That's why. Now, but I think if you try out with R later, if you have a chance, suppose I look at the cholesterol data. I fit cholesterol level versus age. And if I increase, add another regressive variable called H squared. And I calculate R squared. R squared will increase. And if I want to study if there's any cubic component, I can add H to the power of 3. And then R squared will go up some more. In fact, every time you add a regressive variable, R squared will go up. What happens is, if you keep on increasing take this cholesterol data example, you can add H to the power of 4, H to the power of 5. So you get more and more complex model, right? And if you add enough regressors, R squared eventually will become 1. It means you can take a line to every point by adding more points, more regressors to it. Increase the power of the polynomial. The polynomial will become so flexible that it will force through every point. Yeah? You can try that if you do not believe what I say. Now, what about, so using R squared to judge whether an added variable is useful or not is not such a good idea. So in general, by the way, test adequacy of model, use R squared, adjust R squared. But now the thing is, suppose I have my cholesterol level example. I have H and h squared. Now, I'm thinking, can I improve it further by adding h to the power of 3? Can I do that? Well, one way is I include h to the power 3 and then calculate r squared. See whether r squared goes up or not. Well, you won't be disappointed. R squared will go up. The more you add, the higher r squared is. It will go up. So it's not. So you can't really tell from r squared whether the h cube is really necessary or not. That's why you need to look at r squared. Adjusted r squared use this mean square residue over the variance. Yeah? Sum of square total divided by its degree of freedom. So this mean square residue, this is SST. Now remember, SST, this is a constant for a particular data set. Now the cholesterol level is collected. The Y is all fixed. So this is a constant. This is sigma square h. This is an estimate of the variance of the error. And mean square residue changes with order. That's why we call this estimate mean square residue model dependent. Every time you change the model, you get a different estimate. But if I add a new regressive variable, let's say h to the power 3, then I can check, has the variance of the experimental error gone down? If it has, then I think h to the power 3 is good. If I add h to the power 3, there's very little change in the mean square residue. Then I think h to the power 2 is not a good idea. So basically, I described to you how you can add another regressive variable if you want to. That's the way to check it. But don't worry, in chapter 10, we'll do a thorough study of this approach. So that's what it means. So in general, for multiple linear regression, the R squared to use is the adjusted R squared. Okay? So what I've said, I've summarized it here with my own notes so you can study it. So let's look at the example here. The delivery time data. So I fit a model and so I use the statement summary. Summary will give me the adjusted R squared. There's very little difference here. Okay? This is the R squared. This is the adjusted R squared. Yeah? Sometimes, most of the time, it's actually not too different. Yeah. And for the cholesterol data, let's take a look. So here, I have a straight line model. Yeah. And here, I have a quadratic model. So for the straight line model, the R squared is this. For the quadratic model, the adjusted R squared is this. So by adding the quadratic term here, I have This adjusted R square has gone up by, I don't know, about, it depends on your assessment now. Is 0.89 preferable to 0.83? I think there is an improvement. Okay? But let's just say, hypothetically, if I add this, and this is 0.84, probably it tells me that this quadratic term is not too useful. So you can go ahead and try it out since you have the data set and everything. So you can try at home. Let's say add this model. Introduce a cubic term. See whether you improve the tip of the model. Okay? So that's how you can use R squared and adjust an R squared. So, finally, for this section, we want to see how we can test individual regression coefficient. You see, once you have rejected the null hypothesis when you test the overall model, then the alternative hypothesis tells us that there's at least one of these vectors is different from 0. That's why we need to proceed to now test individual ones. Beta J. And J can be from 1, 2, 3, up to 10. Now, in order to do that test, we need a few things. Number one, according to linear model theory, this test statistics, this is the estimate, this is the coefficient, and this quantity Cjj comes from this. If I remember correctly, yeah, it comes from this. The variance of vectors. Okay, correct me if I'm wrong. If my memory is wrong. So that variance covariance matrix, you can find the J diagonal element, and that would be your estimate of the variance of beta J. So in tutorial 2, in fact, I asked you to do something similar for the simple linear regression model. Derive this, show that this follows a T distribution. So here I'm doing it for multiple linear regression, which is also approved for simple linear regression. If this is true, then simple linear regression is also true. Because multiple linear regression includes simple linear regression as a special case. That's why I didn't want to talk about the proof there. Because everything, whatever you prove here, it will be true for simple linear regression. So once you establish that this has a T distribution, you learn this in, I don't know, ST3131, or more likely in ST2132, how to construct confidence interval. Also in probability, I believe. I also taught that can construct confidence interval and do tests of hypothesis. So these are, how do you do all this? Have already been learned by you in previous courses. That's why I don't discuss them in detail. As long as I know that this follows a T distribution, I can, as long as I know that this follows a T distribution, I can derive these two easily based on the knowledge that you have already learned. Unless you have already written them to your teachers, then go and get it back. Huh? By reading your notes, go return to the teachers after a module is completed. Okay. Next. So, all this theory are very beautiful, but it's useless if you cannot apply to a data set. And that's when R comes in. So here, I have a model. So SSR, what's the degrees of freedom? 3. Because when test beta 1, beta 2, beta 3. SSR refers to testing this 3. Degree of freedom is 3. Now, to do it in R, you can use a summary statement. Summary statement will allow you to test each individual regression coefficient. And confidence interval will allow you to construct confidence interval for each one of them. So that's what you need to do in real life. So again, I have done it 2 different ways. Here, using first principle, and here, just apply 2 black boxes. These are 2 black boxes. You just apply, you know what to do. This is from first principle. So you can go through it, and at least you know how all these values are obtained. To give you the confidence when you look at the output. When you go to work next time, don't use this. Use this. Okay? Because you're going to spend time deriving it from first principle unless you have to. So, summary. So in summary, you will see the key statistics. You see the estimate. Beta naught, beta 1, beta 2. So here are all the betas. So for example, if you want to test beta naught head, or beta 1 head, or beta 2 also can. And this is the t value for testing beta 1 equal to 0 versus beta 1 not equal to 0. And that is the p value. So p value in this case is very small, close to 0. So I know, so from this test, I know that I will reject H0 and say that there's evidence that beta 1 is different from 0. For beta 3, it's also very small. So I also reject the null hypothesis that beta 2 is equal to 0. So this one is for testing. Beta 2 equal to 0. This one is for testing. Beta naught equal to 0. As you can see, beta naught is usually not 0. Yeah? Of course, in some situation, it could be close to 0. And this is the adjusted R square. Yeah? Is this a good model? I think so. At least I can explain 95% of the variation in Y using this model. And if you want confidence interval, you can use the function CONFINT to do it. Yeah? Just apply this function. You will get the 95% confidence interval. You can change it to 99 or whatever level that you want. And here it is. So if any of this interval contains 0, then there's evidence that then you do not reject H0. Okay? So that's what it is. Okay? So that's the end. So what have we done today? Well, today we look at a very important decomposition. In fact, this decomposition variance is the basis for your analysis of variance table. Make sure you understand how you get these two equations. These are fundamental. They are of fundamental importance. Alright? And then I talk about testing overall to the model. Testing all the parameters at one go. And if you reject the null hypothesis, then at least one of them is not zero. With such evidence. And for assessing the overall adequacy of model, use the adjusted R-square. Why? Because if you can choose a model that minimizes, somehow give you a very small mean square residue, which is an estimate of the variance of the error.
Sorry?
It's a good model. So if adjusted R-square is close to 1, then it's a good model. And then finally, if you reject after testing the big model, you find that the model is significant, then you can do tests on individual regression coefficient. I think I will stop here today. And then we will continue with chapter 3D this coming Thursday. Don't miss it. It's kind of fun.